You are able to see the screen?
Yes, sir, we can see.
Okay, now let me start with this lesson. And so this is machine design second, MEC 602. And this course is second course of machine design. Already you have gone through first course of machine design at 5th semester, and this course is machine design second course starting 6th semester. And the course designation is MEC 602. Now you can see here in this there are 4 lectures per week, and I have given full address, my contact details in this first PPT. And before this, I have already uploaded this PPT on your website, in a Institute website, and also on. I have shared these PPTs on WhatsApp. Now today's lecture we will mostly spend on the we will discuss the numericals on belt. Previously, I had given you one numerical which was from book. Today's numerical is my own designed numerical which you have to solve with me today. So let me go to the first tutorial problem wherein I have already given you COs and POs. Now in this you can see the COs and POs. COs are course related, while the POs is the program outcomes. CO is called the course outcomes related to the courses which you have studied or which you have to study in next 4 semesters. And you can see here that CO is course outcome which is related to the course. And whenever you study some course, you must ask the question, why I am studying this course, what for I am studying, and what is the objective of this course. And in your life also, you must ask this question to yourself, that this why I should do this job and what is the purpose of doing this job. So there are many COs in your courses which have been taught and which should be taught during your next few semesters, and these course outcomes will lead to the program outcome which is your BTech in mechanical engineering. Okay, now for this machine design course I have 3 COs: CO1, CO2, CO3. You are able to see this slide?
Yes, sir.
Are you able to see this slide?
Yes, sir.
Okay, so
Yes, sir. Yes, sir.
analyze the stress and strain on the mechanical components. CO2 is demonstrate knowledge of the basic machine elements used in machine design. CO3 is design machine elements to perform functions in order to obtain desired objectives under various operating conditions. So first 2 COs are quite well known to you and you can understand them very easily. That the third CO which you will just be familiar with during this course, and at the end of this course you must be able to design a machine element for attaining desired objective under various operating conditions. So this is the aim of this course, main objective of this course. So at the end of the course you will be able to definitely design the machine element for various operating conditions. Now I will also give briefly the definition of design. Design is a process to obtain optimal solution to the problem without compromising with quality and efficiency, with minimum cost under specified constraints. So I will add one more term to this definition, that is design solution. Design is a process to obtain optimal solution at minimum cost without compromising with environment, quality and efficiency under specified constraints. And if you have to design, you have to build a mathematical model, and here you can see the mathematical model which consists of function, and function is to be optimized. It is to minimize it or maximize under certain operating conditions, and there are two sets of equations which are used for optimization is functional equation and parametric equation. Functional equations are those equations which are which perform the function. For example, you can see here in this slide, the functional equation is given sigma is equal to m by z, which is used to find the stress when the bending moment is created on the beam. And the parametric equations are z is equal to I by c section modulus, and I is equal to moment of inertia, which is given for the beam, and which is equal to 1 by 12 of bh square. And this is these are used to design the optimal to obtain the optimal design of machine elements. Now, these are then we can use the parametric equations to have the local constraints and obtain the design optimal design solution, local minima or global minima. So this is brief introduction to this design, then COs and the optimal design, which you will be able to learn in the future also how to optimize the design. Now after this we will go to the regular course, which is the design of belts. Yes. Now this is the first slide, design of belt chains, etc. Next few classes to be used to discuss these. Now, as I have given you already slides, now I am giving the brief of the idea given in the slide. So belts and chains are the major types of flexible power transmission elements. Belts operate on pulleys, whereas the chains operate on sprockets. Okay. Now you can see here there's a combination of drives used in case of a system. So you can see electric power is coming from here, and then it goes, then it is driven by the V belt, then gear reducer, then chain drive, and ultimately the machine is run here at the last stage, which is 1, 2, 3, 4th and 5th stage, which is used to perform certain functions. Function may be a pump is here, it may be something else, it may be a conveyor, it may be something else. So the function is performed at this point. While as these is the input power, these are the drives which are used for performing the functions. Now you can see here the nomenclature of a belt drive. Nomenclature of belt drive. So this is the nomenclature of belt drive. So you can see a small sheave with D1 diameter, with omega 1 speed, and theta 1 is the wrap angle. And here you can see the big sheave, that is the D2 with theta 2 wrap angle, and then omega 2 is the speed of this, and this is moving in clockwise direction. Then you can see the span of the belt, which is S, which is unsupported part of the belt, and you can see the wrap angle on the driving pulley is driven pulley is larger than the wrap angle on the driver pulley. So this is driven pulley, this is driver pulley. So tight side of the belt and slack side of the belt. You are already knowing that the ratio of tensile stress on the tight side and slack side of the belt is based on the angle of wrap, and also on the basis of the groove angle, which is in case of V belt. But in case of flat belt, it is equal to angle of wrap and multiplied with the coefficient of friction. So these things are already taught to you in the previous semesters. Now you can see here the types of belts: flat belt, synchronous belt, grooved, cogged belts, standard V belts, double angle V belts. Now these cogged belts are used to increase the flexibility of the belts and also for the accuracy of the power transmission. So flat belts, you can see generally these are used for the some rough uses. You can see in the various flat belts used in the rough use, while the synchronous belts are used for accurate power transmission. Now here you can see the example of V belt drive, and here synchronized belt. So it has grooves which fits over the sheave of the pulley. Now it's a double angle V belt. This is cogged belt, and this is the cross section of V belt and sheave groove. Now here you should note that this is the cross section, and you can see the pitch diameter, sheave, outside diameter, groove depth. Then here's a typical given belt ride out. Belt ride out is given here, which is the belt which is above the sheave, above the groove, and this is groove angle, which is represented by 2 beta always. Please remember, the groove angle is always represented by 2 beta, while the wrap angle is represented by theta. So this is valid in case of the V belt. So please understand this, that whenever you find a power transmission, and whenever you find the ratio of the tight side to the slack side of the belt ratio, you have to use this groove angle and coefficient of friction as well as the wrap angle. Now after this, I am giving you the brief of the equations which are used for belt design. So first is the length of the belt, which is equal to central distance, and then parameters of R, D2, D1, and this is C is central distance. The angular velocity ratio is also given in this case. These are the equations which you can derive, or which you can remember, or which will be given in the design sheets. Now this is angle of contact of belt. Theta 1 is for smaller sheave, that is a driver sheave, and theta 2 is driven sheave. So theta 1 is always less than 180 degrees, while the theta 2 is always greater than 180 degrees. So length of the span, which is unsupported part of the V belt, that is the flat belt, which is S, that is equal to square root of central distance minus D2 minus D1 divided by 2 whole square. So these are the equations which you have to use. Now I am giving the first numerical here, which I have designed of my own, and you can understand how you can solve this numerical. Are you able to see this? Are you able to see this?
Yes, sir.
Okay.
Yes,
sir.
sir.
Yes, sir.
Now this is the first design problem. Design a V-belt drive that has the input sheave on the shaft of an electrical motor, which is normal torque, rated at 45 horsepower at 1500 RPM, full loaded speed. The drive is to a machine tool in a workshop of NIT Srinagar. So this power is given to a machine tool. That means which is a machine which is run in the workshop of NIT Srinagar. That is to be used 8 hours daily at approximately 700 RPM. So various things are given now. You can see here the input power is given, input speed is given, then the conditions of operation is given, then the machine tool is given for which this power is to be used. Okay. Now I have noted down what are the given parameters. Given power transmitted is to be 45 horsepower to a machine tool. Sorry, there is bucket tool written. It is because of some mistake. So it is actually machine tool. Speed of motor is 1500 RPM. Output speed is 700 RPM. So the first step is compute design power by obtaining the service factor. So what is this first design power? This is the power which is actually for which you have to design the belt. So this will be always higher than whatever is the power to be transmitted. Why? Because always the power transmitted is not uniform. It has to take care of certain shocks. It has to take care of certain non-uniformity. So this is based on the operating condition, or which of the machine which you have to drive, or where from the power is coming. So this you can see here the table. You can see here are you able to see this table?
Yes, sir. We can see it.
So this table will help you in finding the rated power, actual power which is to be for which the belt is to be designed. Actual power is to be transferred 45, but if you design for 45 horsepower only, then your design will not sustain at the operational state. So you have to apply the rated rating to this power, then you can get the actual power for which you will design the belt. So you see this on the left side of this, there is given if you have to drive the various machines. So first machine is agitator, blowers, fans, centrifugal pumps, light conveyors. And if the power given to it is by the AC motor, then you have to apply factors which are given in this first row. Then second is generators, etc. Then third is bucket elevators and textile machines. and fourth is crushers, and the last is any machine that can torque. So you can see in the first column, then in the first row, second row, third row, fourth row, and fifth row, you are given the service factors. And here you can see there is given that how many, for how much hour, how much time this machine has to run. So your machine, the is machine tool, which is here in the first column, but in the second row, you are seeing this. So you are seeing that you have to run the machine, which is machine tool. Okay. So if you
Yes.
go to
Yes,
this
sir.
and you see the number of hours for which it has to run is 8 hours. So I am taking here service factor 1.2. Are you able to understand?
Yes, sir.
So now you have to multiply this 45 by 1.2 and your actual power to be transmitted is 54. Okay. This is first step. In the second step, select the belt. You have to select the belt. So belts are actually, as I told you last time also, it is given you in PPTs which I have shared with you. It is 3VX belt, 5VX belt, or 5V belt, or 8V or 8VX belt. Now, you have to select the type of belt, say 3V or 5V or 8V on the base of the table here, and this is based on the power. Rated power, design power is input power into service factor, and which is power is now here, yours is 54. And if you see here, there is RPM. So RPM is 1500, and your belt design will come, which is a 5V belt design. So it will come here somewhere here, isn't it? So if it is say 100 horsepower and speed is 200, then it will be, you have to use 8V belt. If it is say 20 and speed is 1160, then it will come here. You are understanding this? How to select the belt type?
Yes, sir. So
Yes,
will you
sir.
repeat one?
So you can see here, see what is your speed, what is your rated power? 54. So 54 lies here, isn't it? And if, what is
Yes,
the
sir.
RPM? RPM is 1500, and when you go to RPM 1500, this will fall in this zone. Okay. So you
Okay.
can use 5V type of belt. So there is some mistake in writing here. It is actually a 5V belt, which is 70 hertz. That's not the correct. Correct is actually the different type of belt. So you can use, you can select the 5V type of belt for this. Now step third is compute the nominal speed ratio. Speed ratio is 1500 over 700. Now the speed ratio is equal to 2.14. Then the fourth step is compute the driving shear size that would be produce a belt speed of 4,000 feet RPM. Now this setup is very important. Please understand, this setup is very important. And in this setup, you have to select actually the belt design. So far you have done the calculations. Now you have to select the belt design. Now for the belt design, you must know the length of the belt, but length of belt you cannot calculate unless and until you know the central distance, unless and until you know the diameter of the shear, but you don't know any of these parameters at this point. Now as a guideline for designing of the belt, what you should do is that the maximum speed of the belt is to be taken up to 650 feet per minute, or 650 feet per minute. Speed of the belt. Please listen and remember that speed of the belt you have to take always less than 650 feet, unless and until it is mentioned that your belt should have this much speed. So as a guideline, you have to select the speed of the belt 650, less than that. Now you can select here
1,000.
yeah, 650, 400 feet. And if you select this 400 feet, and you can obtain the velocity of the,
4,000.
yeah, no, it is actually
4,000.
no, it is 400. Sorry, I made mistake. It is 400 feet
Right.
per minute as a guideline. So then you can
Okay.
select, because the usually belt speed is more than less than 650 feet per minute. So you can select 400 feet per minute. So this will be as a guideline. Now from this you will start. Somebody is waiting for admitting. I will admit. So there are some people waiting, so I admitted him. Now this is actually guideline. So here your belt speed will where belt design will start. So I will select the 400 feet per minute, and then I will use this equation belt speed, which is Vb is equal to pi d1 n1 by 12 feet. And when I substitute this Vb is equal to 400 feet per minute, I will get the d1 equal to 10.18. How much?
10.18.
Yeah. So here you have only selected what you have selected now. You have selected the belt speed. So this will give you the first design parameter, that is smaller sheave size of the pulley, which is equal to d1 is equal to 10.18. Now you have to see in the step 5, you have to now select the trial diameter of the driven sheave. So you got the d1, but you don't know what is d2. So for that purpose, what you will do is that you will see here, see this table is, you are able to see.
Yes, sir.
So you can see here in the first, there is a d1. D1 is diameter which you obtained as a guideline at 400 feet RPM. So you have to correct this 4,000 or 400. This you will see speed. Then you will see here the your sheave size was how much? 10.18. So you can select 10.2, isn't it? And
Yes,
this is
sir.
d1, and you will see the output sheave diameter is how much? 15.9.
9.
And what is the speed which you get exactly? Actual output speed will be how much?
754.
Yeah, now you have started a design. So your D1 is 10.2, your D2 is now 15.9, and your RPM will be approximately 744, because in your numerical it was given that your speed should be approximately 700. So there is no bar on that. You can select higher speed also. Now you can see here, determine the rated power for the following belt. For this belt, so you have selected 5V belt, isn't it? But I am showing here,
Yes,
these are, now you have to determine the rated power. Rated power for that belt, you have to determine rated power, which is based on sheave diameter.
diameter.
Yeah, sheave or pitch diameter. So you can see here. Now what was your belt? 5V belt, isn't it? So you
Yes, sir.
selected 5V type of belt. Now what is your input speed? 1500 RPM, isn't it? What is your small sheave diameter? Smaller sheave diameter is how much? Yes,
So
please.
10.2.
10.2. Okay. Now, if you see this graph here, just a minute. If you see this graph here, now 5V belt. So exactly you don't have the value for 10.2, isn't it? Do you have?
No, sir.
Oh, now what
No,
you
sir.
do? What you will do?
Sir, interpolation.
Yeah, now we are going for interpolation. So I will show you now for this problem. I have done the, so for you, for a 10.2 in sheave at 1500 RPM, the basic rated power is to be obtained by interpolation method, because directly we cannot find the value of rated power from 5V belt figure. Okay?
Yes, sir.
Please don't talk in between. Somebody is talking in between. Now you see here you can see X1 is 9 and Y1 is 18, X2 is 11, Y2 is 30, and X is 10.2. It is actually 10.18 written here, but it's 10.2. So we get Y value equal to 24 horsepower. So we have got the 24 horsepower, but to this rated power which you obtain by interpolation, you have to add another factor, that is speed ratio and power rated factor. So you can see here, what is your speed ratio? It is 2.12 something, isn't it? So
Mm,
your,
yes, sir.
and your speed is 1500. So your power added factor will be somewhere here. I have added to this, you can see I have added 1.2. So your Y value was 24 and your speed factor which have power rated factor which have added is 1.2. So your actual power rating is 25.2. Are you able to understand?
Yes, sir.
Okay, now go to next. Now you know D1, you know D2, you know rated power for the belt. So you have designed a belt for this, and this is your design, but you don't know how many types of, how many number of belts you have to use for this power. Now you can see specific trial central distance. We can use following equation to determine a nominal acceptable range for C. Now for obtaining the central distance, which is the another factor of design, you have to use this equation, empirical relation. So if I substitute here value of D2 and D1 and D2, your central distance becomes in the range of 15.9 is less than C is less than 18.1 inches. So in the interest of conserving space, let us try C is equal to 25 inches. So I am taking C is equal to 25, central distance at 25 inches. Okay?
Sir, what is the reason?
Because the range was coming in this range, 15.9 to 80.1.
Okay. Sir, if we can take 20 inches,
No, you have to
Is it-
take a little bit higher. You can take 30 also, you can take 20. But you should also see what is the minimum diameter of the this sheave and maximum diameter of
sir,
the sheave.
is it up to us to take this value?
Yeah, but it is better to conserve. It is as a design
Okay.
parameter. You can see it is a design parameter. Okay.
Mhm. Right,
So
sir.
now this is the guideline here given that central distance will be in this range. So you can select any central distance from this. Okay. Now we are through.
Yes.
We are through with the other design parameter, that is central distance. Now I have to compute the length of the belt, because you know now C, you know now D1 and D2, and you can find the length of the belt.
Belt.
So if you substitute value of C, if you substitute D2, D1, and you can get from this equation the length of belt equal to 91 inch. Okay.
Yes, sir.
But now you see it is whatever length you get here, that belt this length will not be may not be available in the actual operating stage at the market. So there are standard belt lengths which are available. So you have to select the standard belt length. Now you can see here that you for selecting standard belt length, what you will do? You will use this table.
Mhm.
So you will use this table. Okay.
Mhm.
Now what is your belt drive? 3, it is 5V. So here it is given that this is these are the lengths which are available for 3V, and this is the length available for 3V, 5V and 8V. So your next length which you got is your belt line length, you got 91, isn't it?
Yes, sir.
But you
Yes,
can
sir.
have 90 inches belt available.
Mm.
Okay.
Yes, sir.
So you can select this 90 inches. Then after selecting this, you can calculate actual central distance, because previously central distance you had calculated on that page, you got the belt length. Now that has got changed. Now you can find the new central length. Okay.
Mm. Yes, sir.
You please understand this. Previously you had used central distance at 25 inches, isn't it?
Mm.
But now you have calculated the belt length, exact belt length, which is given to you in the market. So that is 90 inches. So you can find now exact central distance. So C is equal to B square root of B square minus 32 D2 minus D1 whole square divided by 16. So I will calculate B here on the basis of new length of the belt, which is 90 inches, and I will get here exact value of C. So exact value of C I am getting 24.5 inches. So this is your actual central distance, and this is your actual central distance, and this is the belt length of 90 inches. Okay. Now,
Yes, sir.
you have now obtained central distance, which are very two important parameters for getting the wrap angle θ1. So now you can compute the angle of wrap of the belt on the small sheave. So that is equal to 180 degrees.
कैसा था कल? कैसा था? 20 रुपया किलो.
Just a minute. So this is your, now you can find that θ1. Okay. There is
Yes, sir.
in this. Now your θ1 is coming equal to some parameter, and that θ1. Just a minute. And if you use θ1 here, I am getting θ1 equal to 166 degrees if I substitute the values. So remember, so you will get 160, which is less than 180 degrees, isn't it? Similarly,
Yes, sir.
if you find the θ2, that will be more than 180 degrees. Okay.
Mm-hmm.
Now next we will go determine the correction factors based on the wrap angles. So how you will determine, and based on the belt length. Now you can see here, correction factor angle of wrap, if it is 166, you can get the correction factor here something 0.92. And if the length of belt is 90 inches, you can get the correction factor for 5V belt, which is 0.96 approximately. So you will apply these factors to the rated power, which you got just now, 25.2 horsepower. Actual horsepower of the belt which is available for this power transmission is 22.25 horsepower. Is it?
Yes, sir.
You have to apply these correction factors. Correction factors take care of, because angle of wrap can reduce the transmission capability of the belt to be of power, and also the length of belt, if it is higher, then the power transmission will be reduced. So you can see here the actual number. This belt can drive only 22.25 horsepower. But what is your actual power which is to be driven?
54.
So if you divide 54 by 22.825, your actual you 2.4 belts has to be used. So you will use 3 belts for this power transmission. Clear?
Yes, sir.
Okay, now go further. Now this is your complete design now. So your complete design is input electric motor at 45 horsepower at 1500 RPM. Service factor you have applied 1.2. Design power is 54. Belt is 5V, cross section 90 inches length, 3 belts. Sheave diameter is 10.18 and 10.2 and 15.9. 3 grooves. Output speed is 44 RPM. C is 24.5. This is your complete design of the belt. Okay.
Yes, sir.
What you will do is, now you can take with this, you can take for the numericals on the belt, and you will just inform me if you have now understood, and if you have any question for today's, you can ask me the question.
No, sir, no questions.
So I hope that then I will record this now. I will record this.
Sir, which book should we prefer for numericals?
Yes.
So which book should we prefer for numericals?
For this, you have to consult on the mod book at this time for this chapter. So don't bother yourself. I think if you do this numerical and understood it well, you can second numerical, solve numerical in the book. You can do that, then you can see easily, you will do all numericals of belt design. There will be no problem.
Okay.
Now,
Okay, sir.
also I will, please,
Hello.
now this is the last slide of this belt drive. You should now be able to find the span of the belt, S, which is by the equation. Because you know C, you know other parameters, you can find span of the belt. Also, you should be able to find a relationship for the tensile, for finding the tension of the belt, tensile force of the belt. You know what is the relationship? I think you know the relationship which you can use. That is, the relationship is given in the books, and you can see that relationship. It is between the centrifugal force and the tight side tension of the belt, slack side tensile force of the belt, and coefficient of friction, groove angle, and wrap angle. So you can see that equation. You can find easily the what will be the T1 and T2 ratio. Please do that exercise also. And now I can say here, I will stop this recording and upload it, this video, on the institute website. Also, I will try to put it on YouTube. So today's lecture is over. I wish you all the best for next lectures. Thank you very much.